Hello everyone, welcome to Math 115 College Algebra. In this section we're going to talk a little bit more about domain and range of functions. So remember what domain and range are. The domain is the set of all possible inputs, right? They're the input values of a function. And then the range are the possible output values, right, of a function. So the domain of a function, we're going to assume if we have some equation, right, some function that is represented in equation form, that the domain will be all real numbers, and then check and remove any problems that we will have. And by problems, it's going to be things like we can't divide by 0, right? So the denominator can't be 0. If there's any input values that make the denominator 0, that's going to be a problem. We can't take the square root of a negative value. So if there is any input values that will make the expression underneath a radical a negative, then we have to eliminate those. Those can't be in the domain. So that's what I mean by problems. And there also could be like physical restrictions for the domain. For example, one of them is like the age of a human, right? At least in the year 2026, the input, so if let's say the age of the human is the input to some function, the input, the age, well, first of all, it can't be less than 0, right? So age can't be less than 0 or greater than probably about, I don't know, the oldest person, maybe 130, somewhere around there. Let's say greater than, let's say about 130. So that's going to limit the domain to be between 0 and 130 if we're representing the age of a human. Okay, so that that would be like a physical restriction. What we're most interested in here are mathematical restrictions. So again, one of the most common ones is we can't divide by 0, right? So if we have some fraction, say p over q, q cannot equal 0, right? Because it's undefined. If q is equal to 0, right? That fraction would have no meaning if the denominator was 0. And then if we have the square root of a value, in order for, remember, we want our answers to be real numbers, right? We're restricting ourselves to the set of real numbers. So p, what's underneath the radical, can't be less than 0. It could be 0, but it can't be less. Right, so it has to be non-negative. And why is that true? Because we can't take the square root of a negative number and get a real number output. Okay, so this will make more sense with some examples. So let's do some examples here. Let's say I'm given 3 different functions and I want to find a domain of each of these functions. So first one is just a basic quadratic function, right? So f of x equals 5 minus x plus x squared. Well, there are no restrictions on the input, right? X can be anything, and if you plug in that value, you're going to get one particular output value. So for any input, you get exactly one output. So in this case, again, this is just a quadratic. There are no restrictions on the input values, the x values. So that means the domain is going to be all real numbers. Any real number is fine as an input. And we're going to see in a little bit how to write that in different notations, and especially we're going to use interval notation a lot. But for now, I'll just write it in words. So the domain is all real numbers. Okay, what about the next function? G of x is 1 plus 4x over 2x minus 1. This is like a rational function. Well, in this case, we do have an issue. We know that we cannot divide by 0. So basically, the denominator here can't be 0. So how do we figure out what x value will make that 0? And then we know x cannot, like the domain cannot include the x value that makes that 0. Well, we set it equal to 0 and solve for x, right? So we basically set 2x minus 1 equal to 0 and solve for x. That'll tell us the x that cannot be in the domain, right? Because it'll force that bottom to be 0. So let's do this. So we have 2x minus 1. This is a simple linear equation. I'm going to add 1. We have 2x equals 1. Divide both sides by 2. So x is equal to a half. So basically, x can't be, x equals a half cannot be in the domain, right? So we know that x can't equal 1/2. So the domain, we can say, is all real numbers, right? Anything else is fine. Except x equals a half. Anything else will be fine. Anything else will work. But if x is a half and I plug it in here, I'm going to get a 0, and I cannot divide by 0. Okay, and again, I'll show you how to do how to write this in interval notation later. This third function, h of x, is square root of 7 minus x. In this case, the issue is going to be when the expression inside the radical, that can never be non-negative, right? So another way of saying that is that this expression, 7 minus x, must be greater than or equal to 0. So must be, write that cleaner here. Greater than or equal to 0. So we can just write this as that. So let's actually solve for x. So I'll subtract 7 from both sides. I'm going to have negative x is greater than or equal to negative 7. To get x by itself, I'm going to divide by negative 1. But since I'm dividing by a negative, I have to switch the sense of the inequality, right? And the negative 7 divided by negative 1 is positive 7. So basically, those are the only values that work, right? As long as x is less than or equal to 7, then we're fine. So basically, all the values where x is less than or equal to 7 is in the domain. Okay, so there's several ways we can represent the domain. We could do this graphically. We could write it as an inequality. We could write it as an interval notation. That's going to be important. And we could also use set builder notation, which is basically a formalized way of writing the inequality. So in this case, the inequality is given, right? So let's actually represent this graphically, interval notation, set builder notation. So if x is, remember how to read this, x is greater than or equal to 5 and less than 10. Okay, so graphically, what does that look like? Let's say 5 is here, 10 is here. So it's going to be everything in between, right? All those numbers will work. But I'm including the endpoint 5, so that's got to be, remember, a filled in circle. And I'm not including the endpoint 10, so this is going to be an open circle. In terms of interval notation, remember it's going from 5 to 10, but I'm including the endpoint 5, so I have to use the square bracket. And then for the 10, I'm not including it, so I use a parentheses. And then set builder notation is like this. We say the set. So if I do the curly brackets, this represents like the set. And then the X means all X. The vertical line means such that. And then I put the inequality here. X is greater than or equal to 5 and less than 10. And then close the set. So this is like the condition, basically. So it's read, again, you read this, the set of all X such that this condition holds. X is greater than or equal to 5, less than 10. Okay, what about the next one? The inequality is X is less than 10. So how do I graph that? Well, if this is 10, I want everything to the left, right? So I'll just draw an arrow, means it goes on forever to negative infinity, but it doesn't include the endpoint 10, so it's an open circle. In terms of interval notation, it's basically going from negative infinity to 10, but not including 10. And set builder notation, I could write it as the set of all X such that X is less than 10. And that would be enough to describe it. Okay, question 2 or example 2. I'm given a graph, and I want to let's put that in interval notation and set builder. Well, we can do. Let's just do interval notation and write it as an inequality. So the way that, if you look at this, right, this piece right here is saying X is greater than negative 2, greater than or equal to, right, because it's filled in circle, greater than or equal to negative 2, and less than or equal to negative 1. So X is greater than or equal to negative 2, and then less than or equal to negative 1. Or, and then this piece right here is saying X is greater than 1. It's open. It's hard to see there, but that's an open circle. So, or X is greater than positive 1. So the way to write that in interval notation is this piece I can write as bracket, right? Negative 2, comma, negative 1, bracket, because I'm including both endpoints. Remember the or I write as a union. And then X greater than 1, I'd write as parentheses 1 because I don't want to include that endpoint 1, and I'm going all the way to infinity. And remember, infinity and negative infinity always include parentheses, right? Because they're not really numbers, so we have to write as a parentheses. Okay, how do we determine the domain and range from a graph? Well, simply the domain, so here's an example of a graph, right? Let's say, so here it actually is a filled-in circle. It starts there and it goes forever downward. So the domain is just going to be all the possible input values, right? So in the domain is going to be all these values. And then the I guess it's going to get, the way it's drawn, it's going to become like asymptotic. It's going to get closer and closer and closer to 5, but never hit 5. That's the way it's drawn here. So the domain is from like negative 5 to 5, assuming it gets asymptotic. And then the range is all the output values. So in this case, it's from 5 all the way down to negative infinity, right? This is going to keep going. Actually, it's unclear what this graph does here. The domain might just keep going to infinity as well. Maybe this gets larger and larger, but very, very slowly. It's really hard to tell. Okay, so let's see if we can figure out the domain and range of a few different graphs here. All right, so in this first case, right, remember the domain is the inputs. So it's starting, it looks like the leftmost input is not quite -3, right? It's kind of starting at -3, but not including it because it's open circle. But it's going all the way to 1, including 1, right? So I would say the domain is from -3, but not including it, all the way to +1 and including 1. Right, I'm just going to use interval notation. And then the range, here actually we do include, so the range is going from 0. And why am I saying 0 even though it doesn't include it here, it's open? Because here it touches 0, right? So definitely 0 is one of the outputs. And the lowest value look like is -4. And we always go from smallest to largest. So actually the range goes from -4 up to 0. And it includes both of them, right? So it'd be -4 to 0, including both endpoints. Okay, what about this graph? So there's a graph about crude oil production, 1,000 barrels per day is the output, and then the year is the input. And in this case, it looks like, again, it's hard to tell exactly on this graph, but probably this first value is like 1970. And then the last value may be like, I'm going to say like 2010. It's about 2010. So then we could say that the domain is from 1970, right? And we'll include it to 2010. That's approximate though, because it's hard to read exactly on the graph there. And then the range, it looks like it's going from maybe like 180, 190. I'll say 190, and then the highest value is like 2000, right? So the range is like maybe 190 to 2000, and we're going to assume it includes both those endpoints. Okay, and then the third graph, so this is a graph of the world population, and the y-axis is millions of people, and the x is the years again. So in this case, it looks like it's starting right around 1950, and it's ending, the data ends like 2000. So the actual domain will be from 1950, 2000. And then the range, so those are the inputs, the range of the possible outputs, well, it's starting around maybe 48-ish, something like that, and it may be going to 90. So I would say the range is 48, 90. And again, we're going to include both the endpoints. Okay. Find the domain and range of this function. F of x equals 2 over x plus 1. Well, we're going to have an issue, right, where this denominator cannot equal 0. So let's figure out where it equals 0. Well, if I set x plus 1 equal to 0 and solve it for x, I'm going to get x equals -1. So x cannot be -1, right? Because it'll force that denominator to be 0. But all other x values are fine, right? So the domain is basically all x, right? All real numbers x, except x equals -1. And the way to write that is to say, I'm going to go from -infinity all the way up to -1, not including -1, and in union, not include -1 all the way to positive infinity. Okay? The range is a little more tricky to figure this out. So one way of doing this is to do a graph. So I would recommend like going onto Desmos and graphing this, and it's going to look something like this. that dash vertical line is going to be at -1. Let's say the graph, it looks something like this. Whoops. That's not very good. So this is going to get closer and closer to -1, but never touch it. And then this side will get closer and closer to 0. And same thing here. This actually gets closer and closer to 0, but never touches it. So for the range, it's going to be all y's except 0. Because this never actually touches, it just becomes closer and closer. It's called asymptotic. Never touches 0, and this never touches 0 from the negative side. But any other y is fine, right? So how do I write all y except y equals 0? Well, in interval notation, it'd be from -infinity to 0, but not including 0, union from 0 to positive infinity. That would be the range. Okay, and then this last one, find the domain and range of this function. Well, the problem, again, is not dividing by 0 in this case, but it's taking the square root of a negative number. So we know that what's underneath the radical, 2 minus x, must be greater than or equal to 0. And if I solve this, so I'll subtract 2, I have -x greater than or equal to -2, divide by -1. Remember, since we divided by -1, I have to switch this, so it's less than or equal to, and then -2 divided by -1 is +2. Okay, so what does that mean? Well, in interval notation, so that's going to be the domain. It can only be those x's, right? Any x that's less than or equal to +2 is fine. And in interval notation, I'd write that as -infinity, 2, and including 2 in this case. Because 2's all right? If I include 2, if I plug 2 in, I'm going to have 2 minus 2 is 0. Square root of 0 is 0, and then -0 is still 0. So that's okay. And then to figure out the range, again, let's graph this. If we graph this, because it's hard to determine without graphing it, we're going to get something that's like this. Has a shape like this. So in this case, the range is going to be all y going from -infinity up to 0, right? Including 0. So it's -infinity. Make sure it doesn't look like an 8, right? -infinity, 0, including 0. So that would be the range in this case. Okay, now I want to talk a little bit about piecewise functions, all right, and that'll wrap up this section. So a piecewise function is basically a function in which more than one formula is used to define the output. So if you have, let's look at this example here, example 6. So this is an example of piecewise function. F of x equals, well, it's going to be this piece, x squared plus 2, if x is less than or equal to 1. So if the domain is x is less than or equal to 1, you'll use this piece, just going to be a constant output of 3, if x is greater than 1 or less than or equal to 0. And then you'll use this piece, so this equation, x minus 5, if x is greater than 2. So it depends on what your input is, will determine what output that you're going to use. So let's say you're asked to evaluate this piecewise function. And if I look at the first example, I want f of negative 3. So the input is a negative 3. Right? X equals negative 3. So I go to my piecewise function here. What piece does that fall into? Well, so since it's negative 3, that means I'm in the first piece, right? Negative 3 is less than or equal to 1. So I have to use this piece to evaluate the output. So f of negative 3 is going to be negative 3 squared plus 2. And then this, of course, is 9, right? Positive 9 plus 2, which is 11. All right, what about f of 2? Well, 2 is greater than 1, right? So I don't use that piece. Here, it says if x is greater than 1 or less than or equal to 2. So actually, this falls into the second piece here, right? So what's my output? It's simply going to be 3, right? It's a constant in that sense. Or for that piece, it's a constant. And then what about f of 5? Well, 5 is greater than 2, so I'm going to use this third piece. And if I plug in 5, right, remember it's x minus 5, so I plug in 5 for x, so I have 5 minus 5. I'm just going to get 0 for this piece. So f of 5 is equal to 0. Okay? So it depends on the piece. Right? It depends on where the input lies. Like the domain basically is split up into different pieces is another way to think about it. Okay, now graphically, here, let's see if we can do this. So based on this graph, let's see if we can write the piecewise function. So it's going to have the form like f of x is equal to, and it's going to have, the output depends on the piece that we're dealing with here, right? Now notice the outputs are all going to be constants, but depending on the piece. There's this constant, this is a flat line here, so there's just constant outputs, but depends on the piece. So if I look at this first one, see how this is going from, it looks like negative 5, right, including negative 5, up to negative 2, but not including 2. So that first piece would be x is greater than or equal to negative 5, but less than 2. If that's true, what's the output? Well, the output is negative 3. Right? So f of x equals negative 3 if x is greater than or equal to negative 5 and less than 2. For the second piece, it's going from negative 2, including negative 2, up to 1, but not including 1. So the domain of that second piece is going to be from x greater than or equal to negative 2, and then less than, but not including, so just strictly less than 1. What is the output? The output is going to be a negative 1. Right? This output value is negative 1 for all these input. If x is greater than or equal to negative 2, all the way up to 1, but not including 1, the output is negative 1. And then finally, what is the third piece? Well, it looks like it's going from x equals positive 1, so greater than or equal to 1, all the way up to 5, right? So less than or equal to positive 5, including both endpoints. So that third piece, x is greater than or equal to positive 1, less than or equal to 5. And what is the output? The output is a 2. So f of x equals 2 if x is between 1 and 5, including the two endpoints, 1 and 5. Okay, so that's how you interpret that. And then we can also do this the other way. Let's say we're given the function and we want to draw the graph. Okay, so in this case, right, we're told f of x equals negative 3. It's a constant function if x is less than or equal to negative 1. So what that means is, right, if my domain is less than or equal to negative 1, we're going to find out we don't actually need this filled in circle here, but I want to put it in for now. Then the output is negative 3. So this goes on forever, right, to the left. Right? It's going from negative infinity all the way up to negative 1. Then, actually, let me do the third piece first. If x is strictly greater than 2, the output is 0. So, and I'm not including the 2, right? So I have an open circle here, and in anything, greater than that, the output is going to be 0, so I'm staying right on the x-axis. Right, and it goes forever to positive infinity. And then the middle piece, to deal with that, I'm going to do a little table here to help me plot this. So if x, I have an x and y. If x equals, it's really going from strictly greater than -1, but you're kind of taking the limit as you get closer and closer to -1. So I'm going to include -1. Actually, let me include -1, 0, 1, and 2 as my points. So if x is -1, what is my output? Well, I have to use this part of the formula, right? So if you plug in, let me move this over a little bit. If I plug in -1 for x there, I have 2 times -1 minus 1. That's going to be a -3. If x is 0, I still use that same output. So 2 times 0 minus 1, that's going to be -1. If x is 1, same thing. That's going to be +1. If x is 2, that's going to be +3. So if I plot these, right, if x is -1, it's -3, so that's here again. If x is 0, it's -1, that's here. If x is 1, it's +1, that's there. If x is 2, it's 3, and it's including that endpoint, right? So that's a filled-in circle. And basically, if you were to do more points in between there, it's going to be all the points that line this line here. And again, I didn't do a good drawing. Should be something like that, right? So notice, because the line actually meets, so it's going to look something like that. The one tricky part, and you have to be careful with this on math because it'll mark this wrong. Because the lines actually meet there, you don't need the fill-in circle. Okay, so I'll say the filled-in circle is not needed. Right, because the first piece, this piece right here, said when x equals -1, the output was -3. So that's right there. And then this piece says when x gets super, super, super close to -1, the output gets really, really, really close to -3. So those two lines actually meet there. And the point is you don't need, here, I'll erase it right now. You don't need that filled-in circle. You can just draw the line going in and the line going in like this. But here you want to include the filled-in circle. Here you want to include the open circle. That's important because there's like a jump there. All right, that will be important when you do the MyOpen Math homework because it'll mark it slightly wrong if you include a filled-in circle there. Okay, so that's it for looking at domain and range. The next section, we're going to talk about rates of change and some behavior of graphs. Rates of change are basically the slopes, right? But we're going to interpret, what that means in terms of word problems as well. Okay, great, thanks.